Everyone, how are you today? Today we are going to talk about a new topic called solid solutions. And solid solutions including two parts. The first part is called substitutional solid solutions. The second part is interstitial solid solutions. As we know, solution involve solvent and a solute, right? So you have solvent and you have solute, and you put solute into solvent, that will become solution, right? So solvent is the element or compounds that is present in the greatest amount, okay? So greatest amount is called solvent. And for the solid material, a solvent atoms equal to its host atoms. For the solute, is that element or compounds are present in a minor concentration. So solute normally has a little amount compared to the solvent. So this, in terms of the solution, you have liquid solutions. How about solid solution? Solid solution atoms are added to the host material. The crystal structure is maintained and no new structures are formed. So the thing is that this is what we call solid solution. You have impurity or you have foreign atoms and put into the crystal. And then, so this is called substitutional solid solution, right? So because this atom replaces the original atoms. Okay? And the important thing is that no new structures are formed. So if the original structure is BCC structure, and you put the atom into this, foreign atoms into this crystal, it still present BCC structure. It cannot change. Okay? And this one is called interstitial solid solution because this atom, the foreign atom is smaller than the original atoms. So the foreign atom will be in the between the original atoms, in the interstitial site. So this is called interstitial solid solution. Of course, the structure, new structure cannot be formed. Okay, so no new structures. So the impurity atoms are randomly and uniformly dispersed within the solid. Okay, so that's what we call compositionally homogeneous. Compositionally homogeneous means this part, the concentration of this is the same as this part, is same as this part. So these foreign atoms distribute randomly in this area. Okay, this impurity distribute randomly in this area. And this is another thing is that solid solution sometimes we call alloy. If you have two metals together, now metal A and metal B, and this will be called alloy. So the impurities in solid, like this is called substitutional, right? Impurity atom. And this is called interstitial impurity atoms. Okay, and if you have more, then now it becomes solid solution. So two types of solid solution. First one is called substitutional solid solution. The second one is called interstitial solid solution. Okay. So solute or impurities atom replace or substitute for replace, this is replace, right? Or substitute for the host. So let's take a look of these two types of solid solution. The first one is called substitutional alloy. Second one is called interstitial alloy. So for example, is that the copper and zinc. The atomic number is 29 and atomic number of zinc is 30. So you have 30 electrons, you have 29 electrons. So they are very close, the size. So this is because the size of copper and the zinc are very close. So this you can replace copper to the zinc. As you can see, this is called substitutional alloy. And if you especially have copper and zinc, especially zinc in the copper, this is what we call brass. Okay, it's not pure copper. It's brass. Because brass is harder than copper itself. Okay? And interstitial alloy, you have, for example, this carbon has six electrons. Iron has 26 electrons, right? So this is how it looks like, is that the size of iron is bigger. The size of the carbon is very small. So compared to iron, the carbon will be the interstitial site instead of the substitutional site, right? Okay, this is what we call interstitial alloy. So if we have carbon in the iron, this is called carbon steel. Carbon steel is much stronger than the iron. Okay, so this is what we call hardening agent to make it very strong. And this is kind of interstitial alloy. So you have two types. The first type is substitutional alloy. Second type is interstitial alloy. Okay, so next term we want to know is called dissolution. Dissolution means that how many solute can be dissolved in a solvent. We want to know the numbers of the solute. So the determination of the solution is there are several figures of the solute and solvent atoms that can determine the degree to which the former dissolve the later. Okay, we want to know the degree how many solute can dissolve in a solvent. So there are four factors which determine the degree of the dissolution. The first factor is called atomic size factor. The second one is crystal structure. The third one is electronegativity. The fourth one will be valences. So you need to consider these four factors. Start from the size first. Think of size first, and after that, think of the crystal structure, and after that, think of the electronegativity, and after that, finally, think of the valences of these two types of atoms. Right. So first of all, let's take a look of the substitutional solid solution, or this rule we need to follow. The rule we need to follow is called Hume-Rothery rule. Right. So let's take a look of the determination of the dissolution within these four factors. The first fact. So this is substitutional, right? Substitutional solid solution. So you have many different. You have many foreign atoms in the host atoms. So first one is atomic size. So this type of a solution only when the differences in atom radii between two atoms type is less than about plus minus 15%. So the size of these two need to be within plus minus 15%. Otherwise, the substitutional lattice distortion and the new phase form. So this one cannot be too small. It cannot be too big. Okay, the foreign atom cannot be too small or too big. Otherwise, the new phase will form. Like if it can change from BCC to FCC, for example. Okay, so this is not the definition of solid solution. Okay, so the first factor is atomic size factor. The second factor is crystal structure. So for appreciable solid solution, the crystal structures for metals of the both atoms type must be the same. What does that mean? This type of the metal, if this type of metal is BCC, this type of metal needs to be BCC. If this type of metal is FCC, then this type of metal need to be FCC. That's why you can make perfect solid solution. Okay, so it must be the same. The third factor you need to think of is the more electropositive one element and the more electronegative the other. So if you have a very different positive one element and very negative another, the greater is likelihood that they will form a intermetallic compound. So you don't want to choose one which is very positive charge, one is very negative charge, no. Or electropositive or electronegative, no. Otherwise, if we put these two together, you will become what we call intermetallic compound. Intermetallic compound is different from the solid solution. Okay? Instead of the substitutional solid solution, you will make intermetallic compound. So what does that mean, intermetallic compound? Intermetallic compound is that if you have this compound, you will have a fixed composition. But when we have the definition of solid solution is not a fixed composition. So you can have any portion of the A atoms and any portion of B atom. You make a perfect solid solution. But for intermetallic compound, you only have a fixed composition. Let me explain this later for you with pictures, so it will be easier for you to understand. So the important factor here is that in order to make a solid solution, you need to have electron activity of this and electron negativity of this very close. Okay? Not too different. Finally, the fourth thing you need to consider is valences. So another factor is being equal. If another factor is being equal here, the metal will have more of the tendency to dissolve another metals of the higher valences than one of the lower valences. Okay, so if we have these atoms like high valences of this atom rather than low valences of this atom. Okay, so the conditions for the substitutional solid solution, let me summarize here for you. This is also called Hume-Rosary rules. First, the delta R has to be less than 15, right? Percent, okay, between these two type of atoms. Okay, the second one is the type of these two atoms need to have the same crystal structure for pure metal. Okay, FCC, FCC, BCC, BCC. The third one is approximately in the periodical table. You need to choose a similar electron negativity. Okay, electron negativity need to be similar. If it's very different in electron negativity, you will make intermetallic compound rather than solid solution. The factor 4 is valency. Okay, all else being equal. This all else being equal, very similar. A metal will have a greater tendency to dissolve a metal of higher valencies than one of lower valencies. For example, this has valencies 3, and this is you have two candidates. One is valence 3, one is valence 2. Then this one will prefer valence 3 here in this position rather than valence 2. Okay. So let's make an example of the copper and the nickel. Okay, let's think of these four factors. So two elements are completely solute in one another or at all proportions. Okay, so this is one of the example, nickel and copper. So for the factor number 1, atomic size factor, radius, copper is 0.128 nanometer. Nickel is 0.125 nanometer. So these two are very close, less than 15% in diameter. Okay, the difference between these two is less than 15% in diameter. Okay, so this bingo, we pass the factor 1. The factor 2 is crystal structure of copper is FCC and crystal structure of nickel is FCC. So of course these two match, bingo. We pass the factor 2. Okay, so you can think of, wow, this is a good combination. They can make a solid solution, right? Okay, so the factor number 3 is electron negativity. Electron negativity for copper is 1.9. Electron negativity of the nickel is 1.8. They are very, very close, which is good. It's not very different. So you can, and then valences is plus 1 and plus 2. So as a result, according to these four factors, copper and nickel can mix to each other in all the proportions: 50-50, 40-60, 90-10. Well, now that's all okay. So you can make this kind of alloys with any proportions. Okay. So this is the question here. This will be 100% showing in your final exam paper. So I want you to remember these questions, and then I might change the elements, and then you find the answer. Okay. So the question 1 is, would you predict more alumina or silver to dissolve in zinc? So zinc is the host material, and you want to put alumina into zinc, and you also want to put silver into zinc. And the question is, which one is better? Which one of these alumina or silver is better to dissolve in zinc? Which one? So you need to think of four factors according to Hume-Rosalie rule, right? First one is the size. So this is alumina and this is zinc. Alumina and zinc, silver and zinc. I will provide this table for you in your final exam. So you need to think of atomic radius need to be less than 15%, right? Alumina, zinc, or silver, zinc, it need to be between less than 15%. Okay, and then next is do they have the same crystal structure? Like zinc is HCP, but alumina is FCC, silver is FCC. Well, they don't match, so they don't perfectly match. Okay, and for silver, the electronic activity 1.9, alumina is 1.5, and zinc is 1.6. Okay, so now you know the answer. Which one is better? Silver or alumina? It's better to dissolve in zinc. Okay, and then final consideration is electronic activity. You want to choose high attendance, high valences, right? Rather than low valences. So the answer will be, let me know. Okay, let me know your answer. Right. So the question 1. Okay, question 2 is copper. Copper is here. And zinc want to dissolve in a copper. Alumina want to dissolve in copper. Which one is better? Zinc or alumina? According to these four factors. Please find out this and let me know your answer. So the substitutional solid solutions of the incomplete solubility is not 100%, it's not all in all proportions, but this can dissolve partially in zinc. This can dissolve partially in zinc. And which one is better? For the question 2, you understand copper and alumina can make perfect complete solid solution. Okay. Right. So next topic is interstitial solid solution. So this is substitutional, this is interstitial. So as you know, the size of the foreign atoms will be smaller. So interstitial solid solution is that the impurities atoms fill voids. Void is the empty space, right? Or interstices among the host atoms. So atomic diameter of the interstitial impurity will be less than the atoms of the will be less than the diameter of the host atoms. Typically, it need to be about half, less than half. So 45% smaller than atoms. So this one need to be smaller than this one, about 50%, 45%. Okay, so for atomic materials that have relatively high atomic packing factor, the interstitial positions are relatively small. It makes sense, right? Because for example, FCC, the atomic packing factor is 74, 0.74. That means 74% of the space was occupied. 74% of the space was occupied by atoms. So you only have 26% empty. And then for BCC, you have 68% of the space was occupied by atoms. So you have 32% empty space. If you have more empty space, of course you can have more interstitial impurities in this crystal, right? So that's why if you have a high atomic packing factor like this, you will have less interstitial position, right? The interstitial position of the FCC is 26%. Interstitial position of the BCC will be 32%. Interstitial position of the FCC simple cubic structure will be 48%, right? However, even though you have 48%, but normally maximum concentration of the interstitial impurity is less than 10%. Right, so let's think of the interstitial solid solution in the case of carbon and iron. This is iron atoms. The carbon atoms is much smaller than iron, right? So for the atomic radius, carbon is 0.071 nanometer. Iron is 0.124 nanometer. Of course, you know the size of carbon is less than the size of the iron. So the maximum concentration of the carbon is about 2%. So you cannot put more than 2% of carbon atoms into the iron. So maximum 2%. Otherwise, you will change the structure, you will deform the structure, whatever. So carbon is the most common alloy materials for ions, but various other alloys elements are used, such as magnesium, chromium, vanadium, and tungstens. So you can put carbon into this, carbon into this, carbon into this, and carbon into this. So carbon and other elements act as a hardening agent. So you want to put carbon here, and you make this material stronger. Iron is not that strong. However, if you put a carbon into the iron, this we call carbon steel, and you make the material much harder. So this is one of example is that you have Ta and the tungsten in, and you put a carbon into this structure, and then the mechanical strength is become harder, higher, right? So let me summarize the point defects in alloy is that two outcomes if the impurity B added into the host A. Okay, so solid solution B in A, and it needs to be randomly distributed. It can be here, it can be here. Okay, and this is all we call point defects. And this one we call solid solution. One of the example I just show you is copper in nickel, right? And this is another example is interstitial solid solution. The case is carbon in iron. Right. I hope you still remember we talked about intermetallic compound. Okay. So this is the example of the solid solution B and A plus the plus particles of a new phase. This is the new phase. Can you see that? The red B, the B is here, A is here. This part is the packing of these two type of atoms are very different from here. These are randomly distributed. This atoms is not randomly distributed in this area. So this is what we call intermetallic compound. So usually for a large amount of B will be distributed in this area. Okay. So this is what we call solid solution. And then this is what we call second phase particle. And in this case, intermetallic compounds. As you can see, this intermetallic compound is very different from solid solution. So different compositions. The composition of this area is fixed. Need to be red, gray, orange, red, gray, orange, gray. So the composition is fixed. And of course, you can see this is different structures compared to this one. Okay, this may be FCC, FBCC, but this one is not. Right. So we finish the first part of this imperfection, which is zero-dimension imperfection. There are 4 topics. First one is substitutional. First one is valency, right? Vacancy. Okay. The second one is called self-interstitial. You have the same type of atoms, right? The third one is substitutional impurity. The fourth one is interstitial impurity. Okay, and we are going to talk about dislocation, which is linear defects, very soon. Okay, and let me summarize another thing is that substitutional impurity can be good or can be bad. Okay, you know the bad things. Okay, for the good thing is the dopants. Okay, so if we have a phosphor in silicon, this is what we call phosphor has 5 valence electrons. Silicon has 4 valence electrons. So you have 1 extra electrons in silicon, and this is called N-type semiconductor. Remember, N-type, N stands for negative. Okay, and then if you have boron in the diamond, okay, in the carbon, which is diamond, you make this diamond become blue, very beautiful. Okay, blue color diamond. Okay, if you don't have boron, that will be transparent. Okay, transparent. Okay, so it makes things, the boron into the diamond make it very beautiful. The phosphor into the silicon change the conductivity of the silicon. And this is a good thing about the dopant, good thing about the impurity. Okay, another one is if you don't put this some kind of small atoms, you have alloy, for example, magnesium in aluminum. This magnesium aluminum is a kind of alloy. In Mandarin, we call 镁铝合金, right? 镁铝合金. Okay, this is good. And nickel in gold is also good. Okay, we make alloys. For the bad thing is that if the sodium chloride has a lithium into a sodium chloride, this is contamination, contaminates. Okay, this is no good, right? Okay, this is first topic, substitutional impurity. Second, interstitial impurity. Interstitial impurity occupy the position between the lattice site, right? So this example is that carbon in iron. This is what we call hardening agent, make the iron become stronger. And hydrogen in LaN5. If hydrogen LaN5, this become a compound, we call AB5, AEB5. Okay, what is this? We need to let hydrogen store into this alloy. So this kind of hydrogen storage for the fuel cell. So this is the material important to store the hydrogen. So you need to have a tank for storage of hydrogen using this alloy. And then you have this, if you have this cylinder of the hydrogen, for the hydrogen storage, you can put it together with the fuel cell so you can produce electricity. So this is one of the important materials for the fuel cell application. Okay? So this is good. How about the bad things? If you have hydrogen in the iron instead of the carbon in the iron, that means this hydrogen in the iron it make iron very brittle. Okay, which is not good. Okay, so you don't want hydrogen into the iron. Instead, you want to have carbon in the iron. Right. The third one is vacancy. We learned this already, right? unoccupied lattice site and formed at the time of the crystallization. How do you form the vacancies? Vacancies. Okay, formed at the time of the crystallization, or formed at the severe under the extreme condition like supercooling. Okay, and we already know the self-interstitial, right? Self-interstitial. Right, and finally, important thing is fraction of the vacancy. Okay, you need to know how to get activity energy, right? And how to get the fraction of the vacancy. And solid solution, there are two parts, right? The first part is substitutional solid solution. Second part is interstitial solid solution. So substitutional solid solution is there are four factors, right? Size of the atom, crystal structure, electron negativity, valency. Interstitial solution, you need to consider the size of the impurity and the host. This needs to be less than 45%. And generally, the maximum concentration of impurity atom will be less than 10%. And final topic is intermetallic compound. Right. So the next topic will be specification of the composition. You know, when we talk about alloy, when we talk about solid solution, that means that you have two types of atoms and put it together. And in that case, we want to know the composition. Okay, composition of A and B. And also we want to know how to, if we have different units, how can we do the conversion? Okay, so composition is that we want to know how many zinc in the copper, right? And then by what definition, or how many numbers of the carbon in the iron atom, iron crystal structures. So the composition, or sometimes we call concentration of an alloy in terms of its constituent elements. Okay, constituent is that the host. So two common ways to specify composition. You need to specify by weight, or you need to specify by numbers of the atom. Okay, you use weight percent or atomic percent. First, weight percent. The basis of the weight percent or the mass percent is the weight of the particular elements relative to the total alloy weight. That's easy, right? I'm sure you learned this before when you are in high school, junior high school. The weight percent is defined as this. Composition is M1 divided by M1 plus M2. M is the weight of the element. That's easy. Atomic percent is what? Is you want to count by moles. The basis of the atom percent calculations is the numbers of the moles of the element. Of course, if you think of numbers of the moles, that means the numbers of the atoms, right? That's the same, because 1 mole equal to 6.02 times 10 to 23 atoms of an element. Okay, is related to the total moles of the element in alloy. So for example, the concentration of the atomic percentage of the element 1 in the alloy containing 1 and 2 atoms. So the definition will be like this: C1 prime will be equal to the moles of the M1 divided by the moles of the N1 plus the moles of N2. So you can use copper and zinc as an example to calculate the weight and weight percent and the atom percent. So the number of the mole of the element will be like this, right? This is mass divided by atomic weight. Right, so the conversion rate, that's it. So how do you do the composition conversion? If you want to convert the weight percentage to atom percentage, what's the things you need to consider? Okay, so you have weight percentage, atom percentage, percent. How do you convert to each other? Or this is mass per volume, total volume. How do you convert this? So this is easy, so I want to skip this for you. So actually, the conversion factor is what? Conversion factor is this, right? You have mass and you have mole. So the important thing is this conversion factor is that atomic weight. So please do this by yourself. This is a very simple calculation, and I'm sure you can make it. And so how about mass per total volume to the weight percent? Again, you need density, right? This is density, right? Okay, so you put the density, the conversion factor is density, so you can do this by yourself. Okay, so alloy density and alloy atomic weight. So I think I will skip this. This is very easy. I don't think you will see this in your final exam paper. Just basic, simple calculation. Right, so summary for this is you need to know this alloy composition. You need to know the definition by weight, by atoms. Atoms is what? Is for moles, right? And you also, of course, you can also use this total volume, how the mass per total volume. And the conversion factor is density and molecular weight. And all you need to know is conversion. Okay. Right. So I think I finished this topic. So now let's move to the two-dimensional defects. Okay. For the one-dimensional defects, two-dimensional defects, and three-dimensional defects, we all call miscellaneous imperfections. So this is one-dimensional defects. We also call dislocation or linear defects. And the interfacial defects, two-dimensional defects, and bulk or volume defects. And after that is atomic vibration. First one, dislocation, linear defect. So line defect is the linear defect is the dislocation are line defects. Slip between the crystal planes result when the dislocation move and produce permanent or plastic deformation. So once you make deformation, there will be permanent deformation. You won't come back. So this is an example to showing you that the zinc, a bar of a zinc. So before deformation, it looks like this, and once you pull this bar from the top and from the bottom, you'll see a slip steps. You will see it was elongate. Okay, this make this zinc become longer. But if you take a look of this part closely by a microscope, you will see something is what we call slip steps. We are going to show you this later. Okay. So dislocation is a linear or one-dimensional defects around which some of the atoms are misaligned. So dislocation can be, there are three types of dislocation. One-dimensional dislocation is called first edge dislocation, second screw dislocation, third mixed dislocation. So let's talk about edge dislocation first. So this is edge dislocation. Firstly, you have a one line here, which is, as you can see, this is mismatch, right? It was here. You know, it was a line very good here, but this, because you have extra one plane insert into this part. So this is, and then you can move this to the end. So that's why this is called edge dislocation. So when we talk about dislocation, there's one important thing you need to remember. It's called slip and plasticity, which is this. So let's imagine if you have if you have atom packing like this, and you have force from the layer 1 and you have force from layer 2 from the opposite direction. And then you want to move this one more. That is space, this spacing. So that's required yield. We call yield stress. Okay, yield stress. Okay, so when you calculate this theoretically, first of all, you need to break bound of this. You need to break bound of this. You need to break bound this, and then move one forward. So for the theoretically, you have a pair of bonds, a pair of bond strengths. This is called a pair. A pair of bond strengths times the bond density. For example, you have bond density here 1, 2, 3, 4, 5, 6, 7. Right? Okay, this is called bond density. For the top layer on the layer on the top on the surface. Okay, this is called, you want to calculate this yield stress. However, when you start to measure this, you want to move this one step. But the yield stress is about 10% of the theoretical yield stress only. And scientists or engineers start to think why? Because it requires you have a pair of bond, so you have bond energy 1, 2, 3, 4, 5, 6, 7. But when you move these two plates to this direction, you only take about 10% of the theoretical calculation strength. Why? So in 1934, the Owen, he's a professor in MIT after this, is that he realized that his explained is that this called plastic deformation could be explained in terms of theory of dislocation. So he used a theory of dislocation to explain this. Why? So let's think of this slip is also what we call edge dislocation. Imagine if you have a carpet and you want to move carpet one step ahead to the front. And you have a lot of frictions between this carpet and the floor. So if you want to pull this way, you have to use a lot of force because the friction is a lot here. So after that, you do the calculation. If you do the theoretical calculation, yes, it takes a lot of energy. You need to use a very big force to pull this carpet to this position. However, practically, you don't do it in this way because you don't want to waste your energy. So you will make it like this. You move a little bit forward first, and move a little bit forward, move a little forward, move a little bit forward. And in the end, you'll reach your target. It looks like a worm walk forward, right? The worm, if the worm want to move forward, you will move one step first, one step first, and one step first, and one step to the front. So this is the theory of the edge dislocation. If you want to move all this one step, you move one by one first. You don't do it all in one go. So this is what we call edge dislocation. So I have animation for you and let you see that how it looks like. Again, if you want to move this forward one step, you don't move all in one go. You just move one by one, 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 and in the end you will reach your target. So let's take a look of the animation first. This is called model of the slip by movement of edge dislocation. It's what we call the yield strength. And it takes about 10% of the theoretical calculation only. Right? That's because they move in this way, what we call slip. Okay? So it's like Newton. It's like Newton condo. You see that the electron move from this one. For example, it's electron conductivity, electrical conductivity. The electron then goes through from here to here directly. Instead, electron stop here and then kick one electron from the left-hand side to the outside. This is what we call Newton condo. So dislocation is that the line defects formed by the mystery of the atoms to reduce the bond density. This is the slip is also the dislocation, right? So the cube and hexagonal metal, the plastic deformation by plastic shear or slip, where one plane of the atoms slide over a adjacent plane by defect motion. So this is the definition of the dislocation. Okay, you move one plane, one plane, one plane, one plane. So if the dislocation doesn't move, the deformation doesn't occur. This is what we call deformation, right? Okay, deformation. So you want to use force to make this material deformed, and you need to use force. And the force we calculate is about 10% of the theoretical value. So this is the dislocation. So if dislocation doesn't move, the deformation doesn't occur. So dislocation can move if the atoms from one of the surrounding planes break their bonds and rebound. Break bond, rebound, break bond, and rebound, with the atoms at terminating edge. Terminating edge is here, right? Break bond, rebound, break bond, rebound, break bond, rebound, and until it reaches the terminating edge. So in fact, a half of the plane of the atoms is moved in response to the shear stress by breaking and reform a line of the bond. This is a line of the bond, right? One at a time. One at a time. Okay? Not every line, all the lines of the bond in one go, but one at a time. So the energy required to break a single bond is far less than that required to break all the bonds on an entire plane of the atoms at once. Okay? So this is what we call edge dislocation. So an edge dislocation is a defect where an extra half plane of the atoms is introduced midway through the crystal distortion nearby the plane of atoms. Okay, this is one. If you take a look at three-dimensional, this is a plane, right? An extra half plane. Extra half plane. You just insert here. Okay, so we have definitions. This one of this the term is called edge dislocation line. What's edge dislocation? Edge dislocation line is this one. Okay, edge dislocation line is a linear defect that centered around the line that is defined along the edge, the end of the extra half plane. This extra half plane, right? Extra half plane. Perpendicular to the plane of the page. This is the page, right? This is perpendicular from outside to this page. So this is perpendicular to the plane of the page. Okay, so this is the dislocation line. So another things you need to remember, this dislocation line, right? This is what we call Berger's vector. Berger's vector means that if you move one space, one unit, this is the direction and the length, or of course you call vector, right? Direction and length, the vector, okay? So represents the magnitude and direction of the lattice distortion of the dislocation in the crystal lattice. Right. So this is what we call dislocation line vector. This is direction of Berger vector. How about distortion? So within the region around, this is extra plane, right? So you have distortion in here and distortion here, above this plane and under this plane. Okay, the distortion. The distortion is that the atoms above this location line, above, right, squeeze together. They are very close, squeeze together. They are very, very close. But here they pull apart, right? The atoms below the dislocation line, this is pull apart. Because your extra plane, right, it's squeezed together, it's pull apart. So the magnitude of this distortion increases with the distance away from the dislocation line. So distortion here will be less the distortion degree here. You have serious distortion, and you have less distortion far away from this dislocation line. So the motion of the edge dislocation is that I just told you. Dislocation allows the atoms of the glide. The glide, this glide. Okay, the glide is this direction. So the glide is this one. The half plane moves from here to here. Okay, so the conservative motion of the dislocation on the slip plane, this direction. Okay, so no conservative is called glide. The motion of the dislocation to perpendicular to the slip plane. This slip plane, right? So it goes to this way. So this go to this way, this way, this way. Okay, this is called climb. Show you here edge dislocation line glide this way, right? Climb is this way. So one of the example in our life is this the three cone. You see that this is dislocation plane. You see that it was here, it was like this. You have extra plane in the middle, right, in here. So this is the edge dislocation line. And like your fingerprint, this is H. You have one insert in this place, so it's dislocation, right? Dislocation. Right. So the second topic, the second dislocation and third dislocation, we are going to introduce you here. The second one is called screw dislocation. Why is screw dislocation? If you have a plane here and then one moved, the burger vector will move one unit, and then for the form by shear stress that is applied to produce the distortion. So you have different dislocation now. So the upper form region of the crystal is shift 1 atom's distance. So this upper form region is shift to the right 1 atom distance. This is 1 atom distance. To the right relatively to the bottom portion. This is bottom portion. And the bottom portion doesn't move, but the upper portion moves 1 distance, 1 atom distance. So if we take a look of this two-dimensionally, you know this upper plane move 1 distance to the right. So as you can see, the empty circle is, or we call open circle, is the atom's position above the slip plane. Okay, this is above, and the solid circle is below. So it's bottom up, bottom up, bottom up, bottom up, bottom up. So it looks like what? It looks like a screw. Look like screw. So that's why we call this a screw dislocation. So this dislocation is linear and along the dislocation line A and B. So AB, 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 AB. Okay, so you use symbol like this. The screw dislocation, this one, derive its name from the spiral or helical path of the ramp. Up, button, up, button, up, button, up, button, up. So it looks like screw, right? Okay, so the third one is called mixed dislocation. So mixed dislocation is the most dislocation found in crystal materials are probably neither pure edge nor pure screw. So in the real case, it's very difficult to find is in this edge dislocation or screw dislocation, but they are all mixed. Okay, but inhibit components of the two types we call mixed dislocation. So this is one of the example of mixed dislocation. As you can see, this is screw dislocation, right? And you have ultra plane here. So this is edge dislocation. This is screw dislocation. So screw dislocation from here and then become edge dislocation. So this is what we call mixed dislocations. Okay? So if we have two-dimensional explanation, you will see that up, down, up, down, up, down, up, down. Down, up, down, up, down, up, down, up. So this screw, right? And you have extra plane here. So this is edge dislocation, screw dislocation. So this cartoon show you very easily if we are from screw dislocation to the edge dislocation, and you want to make it perfect, and you need to give energy to this system, right? So this is the motion of a mixed dislocation. Right, okay, just for your information here, edge dislocation and screw dislocation. Right, we already know the Berger's factor Burgers vector is the magnitude of and direction of the lattice distortion associated with a dislocation line. So that's why we call Burgers vector. So Burgers vector is Burgers vector. Burgers vector including two important information. The first one is the direction, right? Direction. Second is magnitude. Right? From metallic materials, the Burgers vector for dislocation will point a close-packed crystallographic direction, will be of magnitude equal to the interatomic spacing. So interatomic spacing is the length, the magnitude, right? The length of the Burgers vector. So let's combine the dislocation line and the Burgers vector. Is that the nature of the dislocation is defined by the relative orientation of the dislocation line and Burgers vector. So once you have one-dimensional defects, and two important information you need to address is dislocation line and the Burgers vector. Okay? So for the Burgers vector and dislocation line, for the edge dislocation is perpendicular, right? Perpendicular. Is Burgers vector is direction, but edge dislocation is from the front to this page, right? So it's perpendicular. For the screws dislocation is parallel, right? Burgers vector this direction and screw dislocation is this direction, parallel. For the mixed dislocation, is not perpendicular or parallel. So this is one of example dislocation observation by TEM. You probably don't know what is TEM. TEM is transmission electron microscope. You can see if you have a very thin sample and you can have electron beam pass through this sample, and we can get an image, projection image, right? And this is what we call transmission electron microscope. So this is what we call dislocation line are visible in electron microscope, micrographics. Okay, and this is an example of titanium alloy. The magnification is about 50K, 51,000, right? Okay, a dark line here is what we call dislocations. So the formation of, we know the formation of vacancies, and also the formation of vacancies is because of the solidification, right, or rapid coolings. However, that's for zero-dimensional defects, but for the one-dimensional defects is the same. So all crystal materials contain some dislocations, but were introduced during what? Solidification or plastic deformation. This plastic deformation is permanent deformation. Or you can have consequences of the thermal stress that result from the rapid cooling. Okay, the same as the zero-dimensional defects. Okay, so once we talk about metal, polymer, and ceramic have the same situation, have the same story for the dislocation. Okay, so let's take a look at dislocation versus the material classes. For metal, that's what we learn mainly. For example, metal can be iron, can be copper, cobalt, can be zinc. So dislocation motion easier because you have metal, right? Metal have free electrons. So the bonding is what? It's non-directional bonding, right? Because metal, the atoms can have bonds in any directions. So close packed directions for the slip. So you have close packed plane and slip goes through the parallel closed packed plane. Okay. For the covalent ceramics, which can be silicon, can be diamond. So this is covalent bond. And covalent bond, the bonding energy is much higher, is higher than metals, mainly, basically. Okay. So motion hard because you have bonds and you have directional bonding. Okay. For an ionic ceramic, which is, for example, is sodium chloride, you have positive charge, negative charge, positive charge. Motion is also hard because the bond energy is high. And you need to avoid positive or negative neighbors. But once you break it, negative will repel. That's why ionic ceramic is brittle, right? Right. So let's take a look of the dislocation with the property of the mechanical properties. We call slip. So what is slip? Slip normally is dislocation move along the closed packed planes in a closed packed direction. So once you have a closed packed plane and you want to move, you need to move with the closed packed directions. What does that mean? Okay, we will explain this by figures for you. Okay, the closed packed plane have the most bonds, the strongest bondings. Because closed packed plane, of course, they have very dense bondings, right? So for example, 111 FCC. So the planar density, for example, this is 111, right? 111. This is the plane. If you see the blue, atoms, this is 111 plane. So the planar density is highest. So number of the atoms centered on the plane, area of the plane. So this is 111, 111, or 111. Okay, so you have bonding like this, bonding, bonds. Okay, this is 111. So this is the closed packed plane, which the bonding energy is very strong. So you cannot, it's difficult to break these bonds because this is the closed pack. Okay, so the 6 bonds create the strongest plane. This is plane B, a plane B plane. Okay, this is strong closed pack plane, strongest plane. And then if we have this plane and you need to move, right? You need to move. So which direction you need to move? This direction, or this plane? This plane need to move to this direction, or this direction, this direction, this direction, or this direction. You will move with the most easy direction, which is closed packed direction. So that's why we need to think of the linear density. Linear density is the closed packed direction because if this had a very tight, very strong direction, that means you cannot move to this. Why? Because this is most dense packing. So you can move only this direction, or this direction, or this direction. So this is 1. So this is 011. This is 011 direction, 011 direction, 011 direction. This direction or this direction. So this is what we call slip. Okay, so closed packed directions, the direction where the atoms touched tightly. So you want to move, you need to move on the highest planar density, and direction go to the highest linear density. Okay, this is what we called slip system. So slip system is, the definition of the slip system is the state of the closed packed plane moving in a closed packed direction. So for example, in this case is a slip move, slip this between A and B plane, right? and A plane is in the layer 3. This is layer 1, layer 2, and layer 3, right? So A and B plane, they move. It's like slip between A and B plane. Okay, in which direction? In 0, 1, 1, 0 direction, or 0, 1, 0, 1 direction, or 0, 1, 1 direction, right? Or 0, minus 1, 0, 1 over bar, 1 over bar direction. This is the family anyway. Okay? So this is what we call slip system. Ladies and gentlemen, please remember what is the definition of the slip system. So slip system is this. Dislocation does not move with the same degree of the ease on all the crystallographic plane. No. You cannot move anywhere. You cannot move as you like. Okay? Of the atoms in all the crystallographic directions. You cannot move any plane or any direction. No. You only can move with the slip system. So the preferred plane which dislocation motion occur is called slip plane. This is the plane for FCC 545. Okay? So in that plane, the specific directions along which dislocation motion occur is called slip direction. So this is a slip direction. You can, if two-dimensionally you look like this is a closed pack, right? This planar density is highest. And you go to this direction because the linear density is the highest. This is not the highest linear density because there's space. Okay? This is not highest direction because this is not a closed pack. Okay? The combination of the slip plane and the slip direction is termed slip systems. Please remember this. So for the slip plane and direction, this is crystal structure FCC, BCC, and simple cubic structure. Okay, these are the three simplest case. This CN stand for coordination number. Remember? Okay, coordination number for the FCC there are 12. You have 12, right? This 1, 2, 3, 4, right? 5, 6, 7, 8. In the front, 9, 10, 11, 12. So there are 12. For BCC, coordination number is 1, 2. This one for 1, 2, 3, 4, 5, 6, 7, 8. Right? Okay. For the coordination number 1, 2, 3, 4, 5, 6 in the front. So it's 6. So highest density plane. You want to see the planar density, right? Planar density. The highest planar density 111. This is 111. Okay, the closed pack direction is 110. 110. Okay, 110. 110. So you can just move in this direction. How about BCC? BCC is that the coordination, the highest packing density is 011. 011. What's 011? 011, right? 011. Or 110. That's the same. Okay, and what's the closed pack direction? 111. So this is highest plane density, highest density plane, and the closed pack direction. For a single cubic is 001, 001, and then 110 or 100. Okay, this is the sleeping system, right? Sleeping system is this. So as you remember, we talked about sleep steps. This is the zinc, a bar of zinc bar. If you pull from the top and from the bottom, you'll see something like you make the zinc longer. However, if you take a close look of this by microscope, it might look like this, and this is what we call slip. Okay, so this is slip plane, and this is slip direction. This is slip plane, and this slip direction. If you know if you know this slip plane and slip direction, you can realize what is the crystal structure of zinc. So what's the closest packed plane? What's the highest planar density? What is the highest linear density? Okay, then you will know what's the plane of this. Right, so let me summarize that one-dimensional defects. So one-dimensional defects, we call it dislocation. Okay, dislocation. Okay, I think I run out of our time today, and I want to leave this for you for next week. Okay, so next week we are going to talk about interfacial defects. Okay, which is two-dimensional defects. Okay, so I will leave this for the next week. Okay, so that's it.